This section establishes the mathematical foundation for all subsequent problems. It introduces two key governing equations for a Newtonian fluid in a square depth of half width V, as you can see here. Equation 3b, 3.1, which is given in the book BSL, is a velocity distribution. It defines the local velocity Vz at point x comma y within the cross section. And equation 3b 3.2 is a mass flow rate equation, also known as the Burker's expression. To calculate the total mass flow rate W, the coefficient 0.563 is highlighted as a precise value derived from integrating this velocity profile. Now, problem number 1, maximum velocity calculation. This page demonstrates how to find the fastest moving part of the fluid. As you can see the problem statement here, the key concept here is in a duct, friction at walls slows the fluid to zero, that is the no slip condition. The method used here is by maximizing the coordinates here, xy coordinate, at x equals to 0 and y equals to 0 here. The solution proves that the maximum velocity occurs at the exact geometric center, that is 0.0. As you can see here, by solving this problem, taking these assumptions like steady flow rate, fluid is a Newtonian, flow is laminar, incompressible fluid, no slip boundary condition, gravity effects are negligible, and by substituting all these known values in the given formula, we can get the final answer as our maximum velocity 1.25 meter per second. Now coming to the second problem, which is based on a mass flow rate determination. As you can see here, the problem statement on oil with density here 900 kg per meter cube, viscosity is pumped through a square duct of this equals to 0.02 meter. The length of the duct is 10 meter long. Pressure difference is given. We have to determine the mass flow rate. This section focuses on the total amount of fluid moving through the duct. Key concept here is that it explains the origin of Burker's equation, while a basic integration of the velocity profile yields a coefficient of 0.0444. The more accurate value of 0.563 is used because it accounts for a full infinite series expansion. Here we have taken the required assumptions such as steady state, fully developed laminar flow, Newtonian fluid with constant viscosity and density, no slip boundary condition at core wall, rectangular square duct with half width V on all sides. Pressure gradient is uniform along the duct length. By substituting the values here, we will get the final result. Like pumping oil through the specified duct results in a mass flow rate which is approximately 1.889 kg per second. Now coming to the third problem, it is about the local velocity mapping. It teaches how to find velocity at a specific off-center point. As you can see here, the problem statement, maximum velocity at center of square duct, as we derived in previous problem, is at the center, exact center, where x, y are 0, 0. Remember to be we find in the previous problem 1.5 meter per second. Now here we are calculating the local fluid velocity at x is equals to v by 2 and y equals to v by 2. Key concept here is that it introduces the dimensionless ratio. As we go forward in this problem, we will derive one dimensionless ratio by dividing the local velocity equation by the maximum velocity formula. This one. We get a ratio that depends only on geometry and not the fluid's velocity, viscosity or pressure. As we will go further here in this problem, when we are taking certain assumptions like velocity distribution follows exactly lambda and fully developed Newtonian flow, no slip at walls, symmetry about the center. The given max from previous problem, fall in 1.5 meter per second, corresponds to the true maximum at x equals x comma y equals to 0 comma. And by substituting these values, we get this velocity ratio, this local velocity upon the maximum velocity. And here we get the final answer. The result is like at the quarter point where as we've taken here x is equals to b by 2 and y is equals to b by 2. It is a quarter point. The fluid moves exactly 56.25% of the maximum speed, or you can say it by calculating 0.845 meter per second. Now coming with the fourth and the last problem, which is based on the required pressure gradient. Here you can see the problem statement is to maintain a mass flow rate W at 0.01 kg per second for water having density and viscosity given through a square duct of half width B equals to 0.005 meter. Then we have to find the required pressure drop for unit length, or you can see the pressure unit. Here we are using the 3.2 equation or the Burkhardt expression, you can say. This example actually determines how much push or pressure is needed to maintain a specific flow. Key concept for this problem is the formula is rearranged to solve the pressure drop per unit length. Validation for this problem is that crucially it includes Reynolds number check. As we go further in this problem, we'll see this Reynolds number check for the verification of laminar flow. Since here, after computing all these things, we'll get Reynolds number equals to 1000, which is less than 2300, which confirms or validates that the flow is laminar. Means our assumption is validated here. So the assumption that the flow is laminar is mathematically justified here. And the result, we are finding pressure gradient, pressure drop across the length is 28.42, as you can get. These are the final results. Concluding for each function, maximum velocity, mass flow rate, local velocity at here all the point is calculated, and the pressure gradient or the pressure drop